Hello sir and everyone. So in this video I would like to explain about the mechanism elimination and substitution nucleophilic. It is about E1 versus SN1 and E2 versus SN2. But before that, let me introduce myself. My name is Shalana Tamunan with ID student 4213131075. So keep on watching.
Hello everyone, so today we'll learn about some easy technique to assign reaction, whether it will follow nucleophilic substitution or the elimination pathway, and also how to assign the product of the nucleophilic substitution and elimination reaction. So we will search for the quick answer for the such question, and this will help the student who are going to appear for either JAM, NEET, GATE, CSA and NET, or the conventional BC and MSc chemistry student as well. So before we start, we will understand that there is obvious difference between substitution and elimination reaction. And the difference is that the substitution reaction replaces one substituent with another, while the elimination reaction simply removes the substitution. Okay, so there are the basic difference between the two types of reaction pathway. There are more specific difference, of course, that you will need to be familiar with the letter on it. So with this I would like to start, so let's see. So let we begin here with the question, is the nucleophilic or the base strong or not? Okay, so before that, moving into the one side, I like to say that a nucleophilic is an electron-rich species that donates 2 electrons to carbon and form a bond with it, whereas a base is also an electron-rich species, but it gives a pair of electrons to hydrogen atom instead of carbon. Okay, now of course a species can be of both a weak nucleophilic and a strong base. So don't keep in your mind that a particular functional group or a molecule can only be a nucleophile or a base. It can be of both. Okay, so first we will look for the whether nucleophilic or base is strong or not. So this can be have two answers right now. So if yes, it nucleophilic or base is strong, then definitely the reaction is going to follow the bimolecular pathway. That means that the substituent and the nucleophile or base will appear in the rate determinant step of the reaction. Okay, so it can be either of the SN2 or E2. Okay, depending on the reaction condition, we will see that the other way, if the nucleophile and the base is not strong, so in that case we have to screen for the nature of the substance. We have to look for of that, and then I will come into the part later of so on. First move on the bimolecular reaction. So then again we look of the nucleophile or base, but this time we will be looking for whether the nucleophile or base is bulky or not. Okay, now this can to answer, of course. First, if yes, the nucleophile and base is bulky, so that means the nucleophile was strong, and also the nucleophile is bulky, then that definitely the reaction is going to be in an E2 pathway. That is a bimolecular elimination reaction, and then will process and will give the A2 product. And then if not, that means the nucleophile or base is not bulky, so then again we have to go for looking the nature of the substrate. If the substrate is methyl or 1 degree alkyl halides, so in the case the product or the reaction pathway predominantly be the SN2. That is the nucleophilic substitution by a molecular pathway. Okay, and if the substituent is 3 degree alkyl halide, it will be again follow the pathway of the A2 elimination reaction, and if the alkyl halide is of 2 degree in nature, so it can be of the SN2 or E2, either pathway. Okay, so now we see the other way where the nucleophile or base given is not a strong one. Okay, that case we have to look for the nature of the substrate, and if the substrate is of 3 degree or 2 degree or highly stable 1 degree alkyl halide, in the case it will follow the unimolecular reaction pathway. That means that only the concentration of substance will be appear in the rate determining step of the reaction. There will be not the role of the nucleophile or base in the rate determining step of the reaction. So in the case, if the nucleophile or the base is bulky or not, we need to learn that. Okay, so in the case, if there is again two options of the nucleophile, whether it be bulky or the base bulky or not. So if the bulky, the nucleophile or base is bulky, it mostly follow the E1 start pathway. Then even the way part, if the not bulky or the base is not bulky, so that means that it will be mostly follow the SN1 start pathway or SN1 pathway. Now by the start, it means that under certain circumstance of the certain reaction condition that favor a unimolecular reaction, which is involve the weak nucleophile or base, or in the terms of solvent, it can be in presence of the polar protic solvent. Then we will get the mixture of the SN1 and E1 as usually obtained. Okay, now we know that the SN1 and E1 are grouped together because they always occur together. If the leaving group dissociates first, there is an equally likely charge of the nucleophile attacking, so it follows its SN1 route as there is the base pulling of the beta hydrogen that can be lead to the even pathway. Okay, so that is the case mostly there E1 and SN1 in the terms of the nucleophile and base bulkiness. Okay, so here one thing that need to be mentioned, that in the beginning when we talk about the nature of the substrate, when the nucleophile or base is not strong, then if the substrate is of one of the degree alkyl halides and not there are not substituent that going to make that more stable or favorable for the reaction, so the reaction will be unfavorable for either E1 or SN1, so the reaction will not proceed further in that case. one of that. So in this condition, we're going to compare the E1 reaction and the SN1 reaction. So the question we want to answer this video is when we know that we're going to form an E1 product and we know we're going to form an SN1 product. And this is an important question because the E1 and the SN1 reaction have a lot of things in common, and it is probably worth for our time just to review the key things that the SN1 and E1 has in common before we can go about answering this question. Or we will know that we're going to form the SN1 and when we're going to form the E1. So remember, the first step in both of this reaction is that the leaving group leaves, so this is always the first step. And this is the actual step, and the slow step just depends on the concentration of our substrates. So the rate low is always what we say, you know that molecular, it always should know that molecular only depend on the concentration of substrates, and that we're always one, and the E1 and the SN1 comes from, it's that the two that you know that the molecular, and consequently they both go through formation of a carbocation. So in both cases we are going to form a carbocation, and of course carbocation being quite unstable is going to be the rate limiting step in this reaction formation of the carbocation. And remember that the key factor are the determine carbocation stability, while tertiary carbocation are more stable than the secondary, which is much more stable than primary carbocation. So that is what the governs elimination, and the E1 and the SN1 reaction we're always going to favor, they're always going to be faster for the tertiary over secondary over primary. And then let's not forget that also resonance can play a role in stabilizing carbocation as well. And the last factor that the have in common in always have a weak nucleophile or base. So in this case we have methanol is a perfect example of a weak nucleophile or base, and also have example like water or other alcohol. It's always not going to be something which bear a charge, it's going to be natural spacious. Okay, so the thing key which both between E1 and SN reaction have in common, so let's just look at what this reaction has to see what the major product of this reaction is going to be from. That we're going to start answer the question. We're going to see the E1 versus SN1, and then a very typical tertiary alkyl halide substrate for the E1 and SN1 is tertiary, and we also have a weak base or nucleophile, and our product is an SN1 product with just broken carbon bromine. We're forming carbon oxygens, and the other product present in the E1 product. And so what can we tell about the experimentally as a turn? The substitution product is always going to be under most condition a major product, and elimination is going to be minor. So substitution. So normally under normal condition, and we'll just say normal condition, meaning like tertiary alcohol halide with water, nothing else. 8. Substitution SN1 and going to dominate over V1. Okay, so that major, that is minor. Now, however, is the variable which can play a role in favoring the over, and then is the elimination reaction. Are favored more by heat, and maybe it will have to make a little diagram here. So we draw a sheet like this and say this axis the rate, and along the bottom here is the temperature, and then let's say that this is 100% yield, and this is 80%, and this is 20, to keep this a little bit fake here. But our major product at lower temperature is going to be our SN1 product, and as we knew, the increase the temperature, the amount of the V1 or SN1 product is going to decrease. Let's draw like a little bit, so it will be like SN1 as we increase temperature. And for the E1, maybe at the low temperature the amount of E1 product is very small, but as we increase the temperature, we're going to see gradual increase in the amount of the E1. And remember that the E1 favored by temperature because there's more entropy. It's a greater entropy factor in elimination reaction, and there is for the substitution reaction. And if we need to review that the video, that subject, that we can go over there, that more things form an elimination reaction than a substitution reaction. So there's going to be a greater entropy term, and they become important for the thermodynamics of the reaction. So heat is something which we can use to favor elimination reaction or more. So all things being equal, the same low temperature substitution is going the major, but as you increase the temperature, you are going to get more elimination product. So this is one variable which can get changed. Now there's a secondary variable or case, elimination or E1 reaction tend to be favored, and here's an example. So if we take for the example a tertiary alcohol, and we get a strong acid now. This is a strong acid, it's sulfuric acid, and it's also non-nucleophile. What this means that there are conjugate base is this N, it quiet resonance stabilis. This is not likely to attack a carbocation. So in the SN1, remember that we need a nucleophile to attack a carbocation, but if we use a strong acid like H2SO4, which is going to generate our conjugate base of HSO4 minus, this is not going to attack the intermediate carbocation. So we can see that the H2SO4 H3O plus either a reagent will do the essentially amount to the same thing, and this is the elimination product, and this is measure. So one exemption to substitution being favored over elimination, as if you can take a very alcohol in the presence of the strong non-nucleophile acids, and will tend to the elimination as the major product, and also we can see that substitution is going to be minor. So this is one a good exception to know when the comparing between E1 and SN1 reaction. For the next, we're going to follow the last conclusion is the reaction is understand how to tell between E2 versus SN2 by two mechanisms. And the several things we want to use the able to figure out that the most important is the identity of the substrate. In other words, where it's primary, secondary, or tertiary, or primary, secondary. And we know that the primary substrate from that we've seen before favor the SN2 reaction we would have seen in this previous video. And then the tertiary substance favor or E2 reaction. And then now we're talking about the SN2, we're talking strong base and strong nucleophile. And we don't need to worry about the weak nucleophile and bases right now because that one is SN1. And then so all that is going to be considered either strong nucleophile or strong base or both. And remember that we said that typically what is a strong nucleophile and strong base is something like the OCH3, OH minus, or NH2 minus, something that's small or negatively charged. So this guys classify as a strong base and a strong nucleophile. In effect, it's exactly the same thing that down here. So you can see that this is a strong base as a strong nucleophile that we can really tell from the whether it's going to be elimination or substitution. And then the substrate, that's why the substance is so important, is the thing to consider first. And then so our primary substrate, you've seen before primary substance for favor SN2. This guy is a strong nucleophile, also a strong base, but we knew that the primary substance favor SN2, and the strong base and the strong nucleophile favor E2RS, and then we're going to one favor. So this favor SN2 is the can favor SN2 for the easier the two, and so the product that we get here is simply just the removal of the iodine and replacement with the OCH3. Alright, right, simply that's all SN2 reaction is alright, and that is just going there, kick out that gives, and product if you want that show I minus, that would be welcome to do. And then alright, there should be two present dot, not lines. Okay, now let's look at this one. So what sort of substrate do we have here? Well, we clearly have a tertiary substance here. And then we have something that's strong base in a strong nucleophile, so it could be fit to favor either SN2 or E2. So we're going to look at one and see, well, it's the favor. Let's go back. And we know that SN2 is favored by a primary substrate, it's definitely not a primary substance. And then this is a tertiary substance, it's going potentially from the most stable alkyne that we can. So we're going to get to E2 reaction. And the substrate favor E2 the base of the strong nucleophile and a strong base to convey their SN2 or E2, but this can favor E2, this favor A2. So what happened now? And then for the elimination, we have to be a little bit careful and label all for our beta product, because what you're going to be asked on the quiz is, if it's an elimination one, only one you know right the most stable or the major product. And alright, that got the beta one, these two beta 1 carbons are exactly the same, and this is beta 2. So we know that we're going to be seeing an elimination, so we know we're going to draw the 6-membered ring. We know there's going to be a carbon here that the bromine is going to have left. So the question become all is elimination. That are we lose one carbon beta 2? Well, we always lose, if remember according to the states, we always lose the hydrogen from the carbon. That gives the beta carbon, that gives the most stable alkane product and most real stable at most substituent. So ideally, you want to form a tertiary alkane if you can, possibly secondary over primary. And then you can get primary alkanes from just because they're not as stable, they won't form as readily. So one of these types of beta hydrogen will give us a tri-substituent alkane, and the other give us tri-substituent, and the fact is one of the hydrogen from the 1 beta 1 carbon will give us the tri-substituent product that we're looking for. If this can act a base nucleophile, that's elimination, this is going to act a base, so it's going to grab hydrogen, and the carbon-hydrogen bond is going to break phenyl the electron down into the bond between the alpha and the beta carbon and kick out the leaving group. So it's our alpha carbon, and that was our beta 1 carbon. Where is our double bond going to be well across that arrow? So it's going to be here. Right, and then if we to have a drop the double bond between beta 2 alpha, we would have the di-substituent alkane, but this is 3 substituent tools. This would be the major product, and so the product that you will be show, if you want to show the other that the produce again same way we did above, you can, it's not necessary, but you are welcome to this one. And the OCH3 grab the hydrogen, giving us also, and to show that methanol as a product as well. But once again, the most important product, carbo containing product, just are the ones to show right now. And with the we talk about the SN2 reaction potential, the problem potentially come when you have not primary or tertiary but a secondary substance. So let's look at the couple of other here. We have two examples of secondary substance. In fact, that I have exactly the same thing. This is secondary, and this one is also secondary. So as we know that, imagine, because primary favor SN2, tertiary favor E2, more secondary doesn't really favor either. So just as we seen before, we have to look out the nucleophile or base to see what's going to happen. So we just have to ask ourselves, well, that we have to a strong nucleophile in a strong base, or do have something different now. And then we know that because we seen it up here, OCH3 it is a strong nucleophile and a strong base. So this is secondary alkyl halide. Doesn't tell us whether we know that the SN is favorite, so it could be both. And we can see that this is a strong nucleophile and a strong base. It also doesn't tell us which favor. So what we think is might be happen if our nucleophile and base or substitution doesn't tell us which one of the two occur. Then typically what happen is we just see both of these. And And then the both of E2 and SN2 product will see something like this, looking for us to draw a product on which we'll call the E2 product and one which we'll call SN2 product, and we'll just deal which is separately know the E2 product, and then actually let's the SN2 first. That's easy, because since the remember of the SN2 reaction, all we do kick out the leaving group and replace with the nucleophile. But the thing we have to remember, all of we is happen to stereochemistry in the SN2 reaction, and then we know, how we'll know is that the nucleophile attacks from the opposite sides of the leaving group, in other words. And then for the E2 and SN2 product, hopefully it doesn't get messed us up. We can write like this. Okay, and now the leaving group is on the wedge of, cause the nucleophile is going to come on the dice, and it worked. The nucleophile cause the hydrogen gonna be theirs, our product. So we gonna figure out the E2 product have the 5 carbon as we did before, and just be beta 1 and beta 2. And remember that the elimination reaction going to be X for the show that the most stable alkene product. And now it's going to be the result of proton absorption from E2 of E1, well the beta 1, this is right, and the end of chains, the alpha and beta 1. It went between alpha and beta 2 would be a di-substituent alkenes versus. So therefore, according to X set rule, because we want to form the most stable alkane product that we can, that's what we will say. So for a secondary substrate and the strong nucleophile on base from the both elimination and substitution product. The question a little bit less challenging when we have something like now. There are some species that are classified as non-nucleophile bases, or in other words, strong bases, but weak nucleophiles. We talk about the T-butanoside with 2-ring fused amine compound that is a big, bulky. Anytime something that big and bulky through our new cliff nucleophilicity, that window therefore the SN2 product, because such a poor nucleophile and can take SN2 product. It's not gonna be happen in SN2 product because the weak nucleophile and the elimination is going to be happen predominantly, and we still follow the sage, etc. Ultruk and from the most stable team product. So we go, just to summarize, we're talking about the strong bases and nucleophile here. So with a primarily alkyl halide strong base and nucleophile, because primary alkyl halide favor us and CSN2. For the tertiary alkyl halide, if got a strong base in nuclear, for you can get the best a tertiary substrate favor elimination, and the rule applies to form the more stable product. And then we know the secondary alkyl halide is a strong base and strong nucleophile because both of them favor both mechanism. The both occur may not be in ratio 50-50 ratio. That doesn't matter the product. And for the secondary alkyl halide, we have a strong base and weak nucleophile that done without any SN2 reaction.
Okay, maybe that is all about our explanation about substitution, nucleophilic, and elimination.